The universal method of online communication is through the use of classical bits. Secret key cryptography is the most simple example of cryptography, and it revolves around a message and a key. Anyone can see this message, however, this message is scrambled and can only be decrypted if you know the key. The key is something that tells you what to do with the encoded data that is in the message. A simple example would be to switch the first and last letter of the word. Usually, in real cryptography, it is something far more complicated than this. With the inevitable rise of quantum supremacy drawing ever closer, classical encryption on the internet will not suffice. What makes current encryption possible is the sheer amount of computing power for classical computers required to break these messages. But with quantum computers, it will be extremely easy to crack these codes using a specific algorithm called Shor's algorithm. So a new, less vulnerable method of encryption is required. In quantum cryptography, instead of using classical bits to send information, quantum computers use qubits, traditionally photons, to send information via fiber optic cables. It is a method of transmitting information from a sender, canonically Alice, to a receiver, Bob, without an eavesdropper, Eve, gaining any information about the key. The fact that this works is due to the principles of quantum mechanics, namely Heisenberg's uncertainty principle, describing a fundamental uncertainty in measuring a quantum particle. Firstly, Alice will transmit photons through a polarizing filter, randomly giving one of 4 possible polarizations, representing 1 and 0. The photons then travel to Bob, who randomly uses 2 beam splitters to read the polarization, not knowing which one to use for each photon, and guessing each time. Once Bob has read the full sequence of photons, he sends which filter he used for each sequence to Alice, for her to determine which were read incorrectly. Those that were read incorrectly are discarded, and the remaining bits become the key. The simplest type of possible attack is known as the intercept-resend attack. During this attack, an aggressor, Eve, measures the quantum states transmitted by the sender, Alice, and then sends replacement states to the receiver, Bob. In the case of quantum key distribution, this produces errors in the key, shared by the sender and the receiver. However, this type of attack relies on the aggressor guessing which basis a state is encoded in. In 2004, Austria hosted the first ever bank transfer using QKD, and in 2007, the Swiss company ID Quantique provided technology for the transmission of ballot results in Geneva.